So next on the agenda is Mr. Simon Thompson. Simon is a researcher. He's in the University of Kent. His research has covered many aspects of functional programming, including verification tool building and testing theory, Haskell, Erlang, and runs a MOOC, which I didn't know, on Erlang for FutureLearn. He works with IOHK right now on DSLs for Cardano.
Thank you very much.
Mr. Thompson.
Well, thank you very much for that kind welcome, and thank you for coming, and thank you for IOHK for sponsoring the work that I'm going to talk about here. I'm going to talk about a language Marlowe. Okay, that's fine. Yep. So I'm going to talk about a language called financial contracts on blockchain. So the idea is that there's been previous work on describing financial contracts using programming concepts and languages. What I'm going to show is how we've adapted that work to work on blockchain. We've got a language Marlowe, and we have a tool Meadow that allows you to interact, to visualize what's going on with your Marlowe. I'll give you details of the language and what we can do with it. And I should stress, and I think this is true particularly of the presentation about Marlowe, this is work in progress. We've been doing this for a while. We've got to a stage where we're very pleased to present to everyone, but we've got a lot of plans for things in the future, and those I will talk about at the end. So let's get started. I think the best place to start is in the 1950s. If you look back, and then Phil was talking about the prehistory of computing before there were computing machines. I'm going to take this a bit further forward. Look at this is the first business computer. It's a Cambridge team for the Lion's Cake Company. If you wanted to program that, you had to, what you did was simply code that machine. When the next machine came along, if you bought a computer from a different company, you had to learn a completely different language. So you needed specialists to write, program that sort of system. So that's not ideal. And it spurred the development. Though there was resistance at the start, you'll never be able to write efficient programs using these languages that were developed around 1960, Fortran, Algol, and so on. And they were developed to help program the computers that we see there. Often the compiler would be tied to the machine, but you were able to write a program, and perhaps with some ease, you were able to move it to another machine. But you still had to be a coder. You still had to be a programmer. Really, that's the situation today. If you take out your MacBook or whatever and you want to program for it, you write programs in C++ or Java or maybe Haskell. And the situation is similar when you look at blockchain. If you want to write programs to run on Ethereum, you have to use Solidity, a general purpose programming language. So you need to code. So that immediately restricts the availability of these systems for general users. I mean, it's a bit like the distinction between coding on a traditional machine and using something like Excel. We bandy around the figure there are 10 times the number of Excel programmers, Excel users, than there are coders. And I think we could foresee a similar thing in the blockchain world, that we would have general purposes like Solidity, like Plutus, that will allow us to write anything, code anything for the blockchain. But what we've been trying to do is an experiment in looking at something different. We're saying, let's look at people who are actually using the language, or potential groups of users, look at a particular domain, blockchain. And this general approach is called, in the jargon, a domain-specific language. So you build a language that reflects the terminology, reflects the applications of that particular field. So it's to the user. It's focused on the user, not on the technology. And people have been doing these things for a long time. You see them in different areas, and you get a whole lot of benefits from this sort of approach. one nice thing if you look at a DSL in an area which is error prone, to say, I design DSL in the right way, you can rule certain errors out from the start. When you've got your language, because it's working in a more your contract or whatever more easily, and you can make more accurate analysis, specific, not general, you get a whole lot of benefits from that. And just the final thing to say about this, a DSL is a language. So in some ways we can have our cake and eat it. We can take an end language if we wish, use a few features from that. And I'll show you something of that a bit later on. But also because it's what we have our programs, we can execute them. But also in the world of financial contracts, we could give a valuation of a contract. We could look at how we might simplify a contract. Is contract this? Because we're expressing in that specialized language, we have those sorts of possibilities. I hope what I've done in this first part is your motivation for looking at DSLs in this space. Now, what I would say is that financial DSLs aren't new. People have been looking at these for about 20 years. There's a model for this, work by Simon Peyton Jones particularly, but others have followed on from that in using constructs of functional programming to describe financial contracts. And what we've issued here is to take that work, patience of putting these contracts onto blockchain. And I thought just to give you, in order to animate this a bit, I'll give you a simple example of a contract, and then we'll look later on at how it gets modified when it gets onto blockchain. So the characters in these traditionally are always Alice, Bob, and in this case Carol. Bob has a cat. Alice wants to buy the cat, but Alice and Bob don't trust each other. So how can they? But they do both trust that the money gets transferred to Bob only in the case that that Bob gives the cat to Alice. Well, here's a model. Alice puts the money on the table in the contract, if you like, and she waits. She says, am I getting the cat? Hello, Bill. Yes, she gets the cat. At which point she can see she's got the cat. She's happy. Carol can see that. So the two of them, Bob can see that she's got the cat. He's given the cat. Carol agrees with Bob. He's given the cat, and the money gets transferred to Bob. So Carol and Bob here agree. Carol sees that Bob has done what he should do, so he gets the money. If we backtrack, whoops. What's the other situation? Alice puts the money on the table. She waits. She waits. The cat is sitting resolutely there. And she says, right, okay, Carol sees she's not got the cat. She and Alice agree, she gets the money back. So it's a simple, what's called an escrow contract. So you've got these two alternatives. Either Carol can see and concur with somebody, the cat has been transferred, or she can see the cat has stayed with Bob. Examples I show you, but broadly, this is the contract we might expect to see. And in particular, the things I highlight in pink here are the things that allow us the building blocks of the contract. We have an option to say when this condition becomes true, do what the contract here says. So we can wait for a condition to become true. We have a choice here, and what the choice says is, well, depending on what's true or not, we do the first contract or we do the second. But what's nice about that, you can see, I talked around with the diagram before, I showed things moving around, but this gives you a concrete description of what should happen. So we have this language with a small number of these combining forms, when, choice, and pay, and so on, that allow us to build a contract like that. Okay, so that's the second ingredient. We've talked about DSLs, we've talked about financial contracts. The third ingredient which fits into this picture is just to tell you a tiny bit about the Cardano platform, just in case you're not aware of what that looks like. At the basis, we have the Cardano settlement layer. This is the blockchain with a very simple, the settlement layer, not doing complicated transactions. We simply do, we're not doing complicated programming. It's not a general purpose programming platform like Ethereum. It's the law at which settlements take place. And for those of you who are aware of this, the distinction, the UTXO layer, not. So we have the Cardano SL. On top of that, we have Plutus. As Phil explained, Plutus platform is a functional programming platform for writing operation world. We have time, we have randomers, and so on, and we have wallets belonging for people who have accounts containing ADA. And what you can see is that Marlowe fits in here. Marlowe fits on top of Plutus and provides this special purpose access to special purpose language for designing financial contracts. And those contracts can talk about things in the real world, the price of oil, a random choice. I mean, Marlowe is, and it was designed to fit into this stack, but you could also, or indeed, you could see it running on an entirely different platform like Ethereum. It's a general purpose in that sense. Marlowe contracts can be implemented on top of a number of different platforms. But the one we're concentrating on at the moment is running on top of Cardano SL. Okay, so that's given 3 ingredients. We've got the idea of a DSL, we've got the idea of a financial contract DSL, and we've got the Cardano platform. What does it mean to take a contract? What are the implications of saying we're leaving the legal world, we're leaving the world of lawyers and real world fiat currency, if you like, and we're moving to a world of blockchain. So a typical contract in the old-fashioned sense is one which describes what should be the case. It says Alice should pay money to Bob, etc. But if Bob doesn't pay, if Bob doesn't pay Alice when he should, Alice has recourse to the legal system. She can sue him. What can we do to replace that? What we can try and do is build mechanisms on blockchain that will make sure that the right things and contracts will be, which will enforce themselves. So that's one aspect of moving things onto blockchain, which is very nice. Get rid of the legal system. That's not. There might be disadvantages to that, but you can see certainly that would be a good thing. I suppose the other thing, a note of caution, if you like, is the other thing that happens when you look at cryptocurrencies and you're thinking of running things on blockchain. These things are designed not to allow you to spend the same money twice. That's a good thing. You can't, if you have money in your pocket, you can't spend it twice. The problem is that a lot of the financial system depends on you spending money twice. The whole notion of credit allows you to spend money you don't have. So if you move to this self-enforcing model, take the radical credit and so on disappear. So I think you need then external providers of credit and so on and so forth. So it's not without complication in that regard. But we do have, what we have to think about at the moment is concentrating on the first, trying to see how we get how we write contracts in such a way that they're going to be self-enforceable. And there's a very nice phrase that I think has been accredited to Buterin, but potentially to other people. This idea that you have what's called crypto cryptoeconomics. You need to get cryptology to cryptography to make the past irrefutable. One of the key features of distributed ledger technology is that the ledger can't be changed. It's there forever. So the past is protected by cryptography, and then you use financial incentives to shape people's behavior in the future. So it's that combination of, which makes it a fascinating area to work in. And I think the other point to make here, and this is one that becomes crucial, you'll see a bit later on, is that there are two things we need to do in order to shape behavior. We need to make sure nothing bad happens. Obviously, we don't want money to be spent twice, but the blockchain will support us in that. If the contract says money go from Bob to Carol, but we equally well have to avoid walk away. We have to prevent the situation where some money gets put into a contract, and I can see nobody's going to come after this for me, so I simply walk away. We have to design things in such a way that once somebody has signed up to the contract, they are incentivized to carry on participating, or the contract in some other way ensures that their walk away can't subvert what is meant to happen. So that's something to bear in mind. Bad behavior we don't want, but we also don't want to absent them. Okay, so Marlo, I can finally talk about Marlo. And in a nutshell, okay, this is perhaps for slightly more technical. We've implemented Marlo. It's a Haskell data type, so it's an embedded DSL semantic, so it's completely formally specified by writing a Haskell program what this language does. We've got an implementation on the Cardano blockchain. So as it stands, the implementation of Marlo is the biggest Plutus contract working on blockchain. Because effectively what we've done, this is Alex, is on the Marlo team, has written a Marlo interpreter, if you like, as a Plutus contract. If you remember, you could see the Phil was showing the two sorts of code, the code that runs on chain, the code that runs off chain. What we have is the code that runs on chain, and that enforces that Marlo contracts on the blockchain are enforced. They only do what they should do. We've got some work on analysis for these contracts. We're doing some work on proving properties of the contract. And we've got a simulant in this system Meadow, which I'll show you a bit later on. And what we have to think about, I'm not going to say a huge amount about this. It's something that's on the agenda for the Plutus project and for Marlo in the next few months, is thinking about how we deal with oracles, observations, things coming from the real world. How do you generate random values, for example? You want a source of randomness. How do you incorporate that into a contract? I mean, one simple way of thinking about it is that you can model an observation simply as a value that has got a signature agreed by every participant in the contract, and that provides. And in the end, that's what it will have to be. Whatever mechanism you use, it have to be a mechanism which is trusted by all participants. So just saying to participants, you must sign this off in some way, is not a bad approximation of reality. But I'm not really going to say much more about it. For contracts to work, in order to make sure that contracts don't fail, we require people to commit cash up front. So people commit a certain amount of money in order to avoid people walking away. That commitment is finite. So you say, I'm going to put 100 ADA into this contract. And if everybody else involved simply walks away, you will get that money back after a finite time. So our commitments say, you commit for a finite period. We need to, as I say, we need to avoid walk away. But if you think about it, a contract can't require you, contract running on blockchain, or whatever, can't require you to commit. It's not that the modality is just wrong there. So we can't require a commitment. We can only ask for a commitment. And so when we ask for a commitment, if I ask for you to commit 100 ADA for 20 blocks, I have to give you a timeout. I have to require you to answer within a finite amount of time. So not only are our commitments bounded, but our time wait for is itself bounded. If you like, we're not running the contract on the blockchain doesn't make anything happen. It's important to really make nothing happen off the blockchain. What it does do is allow things to happen. So it's permissive. It will, instead of making a payment, what the contract will do is allow you to claim the payment. So it's a, if you like, you're pulling stuff out of the contract. Contract is not itself pushing things to happen in the real world. So commitments, if you like, this is a summary of what we have done to the traditional contract languages in order to make them work on blockchain. So here's our escrow contract. Remember, we've got a when, we wait for a decision, and then we make a choice. How does that vary? What do we do differently in our language? Well, first of all, only wait for a finite time. But what we're doing here is we're saying, when this happens, do this. But what if this never happens? To do that, but we want expressly to rule that out. So we have to think about each of our constructs having this timeout added to it. So we say that happens up to block 90. So there we've got our, so now we're saying we've up to block 90. When this happens, we do this. What happens if we get to block 90 and that hasn't happened? What we have to do is provide an alternative. So we provide the alternative that says happens if we get to it, and we trigger this at timeout if we've not triggered the when. So we add timeout and we add extra actions to our contracts to be executed when timeouts happen. So there's our escrow contract, but we have to do something extra, and I have to show this as it gets bigger. What we have to do is put around that some sort of cash commitment. And here you can see Alice. I remember Alice was wanting to pay 15,000 ADA for the cat. In executing the contract, we put that commitment around it. What have we got in here? We're saying this contract says wait for Alice to make a commitment of this amount. It says make the commitment up to time 100. After that, it can be redeemed. You can get your money back after 100. But it also says this is the time you wait for Alice to make. So we wait up to block 10. Alice hasn't made the commitment by then. What we do is whatever sits there. So our commitments have this combination. Our commitments have themselves a timeout and this here. So what we've done, as I say, is we've taken the constructs from these previous approaches and just embellished them out and added the notion of a commitment. Okay. I can show you Marlo. Here is what I'm showing. This is version 1.3 of Marlo. It's the version that's reported in the paper that we published about this. It's the version that's implemented in Meadow. We are already looking at the presentation here. What's in the paper? What's in Meadow? So what do we add? You can see we've got this commitment of cash. We've got a way of redeeming a cash commitment. We've got a way. So here we're making a payment from one person to another of a certain amount of money. That payment can happen if the person doing the payment is being made, claims it within a particular time, otherwise you follow this contract. So again, with the timeout, we always have the remedial action. And we're able to combine contracts together like that. And that's pretty much it. It's a small, compact language. And this is written, you know, if you read Haskell, you can see it's pretty standard Haskell. And I've just added a couple more examples. This is a futures contract you can think of. Alice and Bob commit a certain amount of money, and then at effectively the delivery date, depending on how it relates to the forward price, then certain payments are made. I've grayed out the bits here which are to do with timeouts and remedial action. So if you like, the real functionality is in the coloured part, and you can see that we've had to add these things. And there's a question that we're thinking about: how easy is it to take a non-analyzed contract and turn it into one that works on blockchain? That's something that we're thinking about at the moment. So we've got a simple futures contract there. This is a deposit incentive contract. So Alice commits 100 ADA, Bob commits 20 ADA. If Alice chooses during the period up to 100 to get her money back, they both get the money back. Otherwise, if you reach the point 100, Alice gets her money and Bob's. So it's a very simple sort of, we call it a deposit incentive. She's getting a reward for leaving her money for that period. And the reason I put this up is I'm going to show you how this works in Meadow in a few minutes. Okay, so like that. Now let me say a tiny bit about what it means to embed Marlowe in Haskell. I was playing a tiny bit fast and loose earlier on when I showed you this contract, because in fact these things like majority, chose, and redeem original are not things that are defined in Marlowe. They're things embedding in Haskell to define. But I think the way to think of these is that they are effectively abbreviations. We're saying here's a name for a little bit of a contract, or they're simple templates. Here's a name for a very simple function or template that generates a contract according to one or two inputs or arguments. So we can just use a very small part of the functional language Haskell to make our contract look that much more readable. So for example, we might pay chosen might be the fact that the majority have chosen the result pay. And we might have that the majority choose an X, like this is the template, this is the function, if two of Alice, Bob and Carol have chosen X. So we're able to build up a top level contract just by writing some simple names, simple naming of contracts and simple variable contracts to give us the top level result. So I think you could take off your users because you're writing programs, but I think if what you think of here is we're just writing abbreviations. A sample of one. I was traveling up a train at the weekend and sitting next to a friend who's a journalist, and he was saying, "What are you talking about on Tuesday?" I said, "Oh, it's this," and I showed him this contract. He said, "Oh, I can understand that." So it's a bit like the sort of formulas I write if I write something in Excel. And I said, "I'm going to quote you on that," because it's. You know, I didn't offer him 20 quid. There was no incentive. There's no financial incentive to get him to say that. So I think what we are doing here is working at the level where we're writing denotational descriptions of simple contracts. And an obvious way of building up a complicated description is to add some simple abbreviations. Okay, so we use them. Now, how are we doing for time? Okay, let me say a bit about implementation. Because we've done a number of different things here. We have inside Haskell we've written a small step semantics for our DSL, so you can run that in Haskell. And if you're comfortable with doing things in Haskell, that's fine. What we've also done is build a tool that allows you to understand more visually what a contract is doing. Now, it's the bane of everyone's life. I know. I'm going to show you this. Let me just describe it a tiny bit of what the layout is here. On the left, we have a block representation of contracts. So what you can see here, for example, these are all the contracts, possible sorts of contracts you can write. And in each of these holes, you can put a certain sort of, some of them require money, some of them require observations, require other contracts. You can build up complicated contracts like this by assembling these blocks together. It's a visual rendering of the Haskell data type. What you can see in the top right-hand corner is the Haskell presentation of that. And if you prefer text blocks, you might think, oh, that's a lot more readable, but we're providing facilities for both kinds of things. Also here, we've got facilities for stepping through understanding how a contract is going to behave. And I will show you that now, I hope. Okay, now this is a bit more, I've blown it up. So what have we got here? We have got, okay, with some of the abbreviations removed. So Alice has become 1 and Bob has become 2. They're just abbreviations. Then they're enumerating the participants. So what we have ways, you can see here, you can convert from the Blockly here to code, you can convert code here to Blockly. You're able to move between those two forms. What else have we got? Well, what else we have is you can look inside the contract, and perhaps we don't want to do that particularly, but we'll see what. But we can provide input, and in order to help you step through your contract, we can tell you which inputs it makes sense to write. There's a manual, you can choose to put in whatever you like, but we're saying, actually, the sorts of inputs you might want to make are these. So let's say at this step, we want to do this action, and then we can execute. What happens there, you can see the contract, you can't see, the contract has shrunk. If you look at the top, we've now got a smaller contract because we've executed the first commitment. We've advanced by 1 block, and then let's make another commitment here. We'll say do that action. You'll see the current block will advance to 2, and you should see the contract up here will advance. So the contract is simpler now, and we're getting different choices, differences here. So let's choose. Should we choose 0? What's the choice going to be? So you can see we have expanded that out, and I'll show you how we can deal with this expansion problem in a second. Let's just make the choice of 1. Let's add that action and then execute. And now what have we got? You can see the contract here, perfectly readable, and we can see the contract up here is readable. And what this is saying is that we're going to redeem both the original commitments, because we made a choice before the contract expired. We were waiting 100 steps, if you like. What we've done here is we're going to redeem. We're allowing both participants to redeem things, and that's the end of the contract. The contract is exhausted now. So what you can do is you can design your own contracts. You can execute single step through them using this visual interface. But the one thing I haven't shown you, which I want to show you now, is that I talked about doing this as an embedded contract. And what we can do is we provide an embedded editor. Oh, now this only works if you run the website. Okay. Oh no. Right. Okay. Right. Okay. The internet, and of course, if you don't run the local web server, your demo doesn't work. Right. I will not try and recover in real time. But what you are, let me explain what you could do here. You get an editor for Haskell. Within the browser, you're able to convert that Haskell, that embedded contract, into a pure Marlowe contract and then execute it in Meadow. Oh, the nightmares of doing. I maybe do it after the end of the talk, but let me crack on with the talk. Where are I? So we've seen that you can interact with your contract in this way. Right, okay, let's carry on. So we've got this in-browser simulation, and we can go right from a Haskell embedded contract through to pure Marlowe, and then through to an interaction. Good. But I think the thing we're most excited about is that one great thing about when it was announced there was going to be PlutusFest, it's surprising how much a deadline moves a project on. I think both the Marlo project and the Plutus project, there's been a lot of checking in on the repositories in the last few weeks. So what we have on the mock chain, this simulation of the Cardano settlement layer, is we have a single Plutus script that will run every Marlo contract. And that's running on UTXO. That's a really stripped down, it's an extended UTXO. It's stronger than Bitcoin, but it's way simpler than Ethereum. You don't have all these processes and potential race conditions and everything else. It's a very simple functional model. And what we have is this our contract language running on that. And it checks it doesn't do anything else. And it's the most complicated Plutus program so far, because it's effectively a universal machine for this small language. We can do some analysis. We can ask questions like, these contracts are all finite, as you've probably guessed. Because we have timeout, we can ensure that the behavior that each contract has is finite. And that's, I think, no due diligence would allow a financial institution to issue things that weren't finite. I mean, there's a lot of restrictions on what sort of financial instruments can be produced. Perhaps not enough in the light of what happened 10 years ago. But the fact a financial contract should be finite is we can take into. So we're able to do, but they may be big. We're able to do analyses using automated techniques like SMT solving to check whether a contract can do something bad. Can it make a failed pay action? And so doing that checking, we can guarantee that nothing bad happens. Work in progress. What are we thinking about? We're thinking about what templates can we produce? What do traditional financial contracts look like when we put them into Marlowe, when we put them onto blockchain with the restrictions that we designed into the language? And we're very pleased to be working with business analysts, because it's not something that we can do as programming language researchers. It's not it's aware of our comfort zone, but we will be working with people to ensure that we get the right set of contracts running on templates for contracts running on Cardano. We need to think, and this is something that one of the things that will be happening in the Plutus world as well as the Marlo world. We have to think about how to charge for running a contract. What sort of charge do we make? Do we make it simpler if somebody uses a template which is already on the blockchain? What happens if people use libraries that are already on the blockchain? There's an interesting set of questions around how you shape behavior of users by the way you charge for executing contracts. We need to think about that. We need to think about syntax. We can write contracts in this format. So Alex has been working, it's one of the team has been working on this. It's a parenthesis-free syntax, which there'll be certain programming communities who will be happier to see this than one which is parenthesis heavy. So, sorry?
The Excel.
Oh, yeah, possibly. Yeah, this looks like Ruby to me, and we got yeah, we can argue, but let's not argue about concrete syntax. No, it's always a good thing to argue about. Yeah, we've added one or two constructs to the language that I've shown you. We've added a simple version of a while loop, which complements the when, and just some things that allow us to write simple simple definitions within Marlowe itself. But we need to think about the design. How much of Haskell do we want to suck inside Marlowe? How much are we going to leave as part of the embedding? So that's a bit of work we need to think about. We're working on formalizing the semantics of this. Pablo's doing a long way towards having a formalization of what's going on in our semantics and proving results in that formalization. So not only can we say, the analysis I was talking about earlier would say for this contract, can it generate a failed pay action? What we can do if we use theorem proving is we can say all these contracts, all this class of contracts will have this good property. And also we need to think, I mean, there are questions about how we, at the moment, there are components to compiling a contract. We've done the difficult bit of putting the on-chain, getting the on-chain code to work, but we need to complete the work on it. And also there are questions about, as contracts get bigger. This is something Agalos alluded to earlier. There are questions about whether we might put some part of the contract, maybe the Cardano SL, but other parts of the contract might sit on a side chain running Cardano CL. So these are all questions which remain to be resolved. Thinking about, I said this earlier, adding commitments and timeouts automatically, trying to find default ways of doing that, and completing that integration with Cardano SL. I think I'm overrunning my time, so I'm going to. Whoa! Oh, that's the trouble with cutting and pasting. That wasn't meant to happen. You might ask the question, why is it called Marlowe? And I thought I would answer that question. Christopher Marlowe is a very famous playwright. He's from Canterbury, as is the language. And he was somebody who died young. He lasted nearly 30 years. If Marlowe's 30 years, but he was also somebody who was entrusted. He was a playwright, but also a spy for Queen Elizabeth I. So he was somebody who was entrusted with valuable secrets. So we thought Marlowe's a thing that was made in Canterbury at one point, so hence the name. To conclude, this is what we've done. We've got a user-focused DSL. We can provide analyses. We can provide guarantees by formal proof. We can do user interfaces. And I think as a final point, I make the point that we see it as a proof of concept for other DSLs. We've shown the model that you can work successfully with a model where we run these in a very lean way. We have a single Plutus contract that executes all the Marlowe contracts. Of course, it might be better to compile individual Marlowe contracts. That's something else to look at. But we can see this as a proof of concept for other DSLs. I think the nice thing about DSLs is that you don't have to do everything. So I think what we've done is explore a design space here, learned some general things, but there might be other languages. Do you want to build a DSL for games, for example? That would require other components like committing to values, secretly committing to a value. To do that. We see there's lots of scope for doing interesting things in this area, and I don't think the more we have, the better. So I think on that point, this is what I've said this already about what we're thinking about for the future. So I think on that point, I will conclude. So thank you very much.
Open it up for just maybe like one question. We have 5 minutes.
We have 5 minutes. Okay, one question.
Okay. Does anybody have any questions for?
Just 10 seconds. We just need to get you on the mic.
Cheers. Hello? Yeah, I was looking at the GitHub repo because I was going to throw it into our app generator for fun before coming.
Right.
And it's like 80 megabytes for JavaScript files.
Right.
So I'm just curious where all that weight's coming from.
thing that didn't work, let me go back and make that work. It's what we're doing is we're running the Glasgow Haskell compiler inside a browser. So we have we're running the Glasgow Haskell compiler inside the browser. So we have a JavaScript. We're running GHC inside GHC.js. Yes? Faye, but yeah, so that's what we're doing. So it's the embedded editor in Meadow that is doing that. We made a design decision in building Meadow that we didn't want to require people to download anything. But in practice, I think what may well happen is if you're using Haskell heavily as the language in which Marlo is embedded, what you will do is just do your development in your ordinary Haskell environment. So you don't need to do the conversion from embedded Marlo to pure Marlo inside the browser, and that will strip out a whole lot of stuff.
Thank you. And I guess as a follow-up is WebAssembly. So I want to create something that users are able to do. So I'm not giving them a server. We're not centralized in any way. So is WebAssembly going to be on the radar for dealing with that issue specifically?
I think you'll need to talk to people this afternoon. I mean, I know because IOHK used Haskell heavily, I think there's some thought about trying to put investment into the GHC.js community. But I know there are also people looking at compiling Haskell, and that could be. And I think the Ethereum people are using WebAssembly for a future. I think I heard the gospel to that effect. So it may well be WebAssembly becomes a big thing space. Okay, yes, one more. What time do we finish?
Hello?
3 minutes.
Okay, so you said you have Marlo interprets a Plutus smart contract.
Mm-hmm.
Is there any intention, at least right now, from IOHK to have the ability to write a Marlo smart contract and then have that compile with Plutus?
Yeah. But given the PlutusFest was coming up, we thought the quickest way to get it working is to have the interpreter.
But is it going to be both? Or like,
I don't see any reason. Yeah, I think we'll try that. I mean, I don't I mean, because again, there are these, and this is technology we've not really thought about. There's a question about how long contracts live on the blockchain, and it may be the compiler couldn't take it for a shorter period. I don't know.
Right.
But yeah, I think there's a whole set of questions about the engineering of this that we've not.
We'll have some time to flush out.
Yeah. So I mean, there are no firm dates in here, but there will be a lot. We hope there'll be a lot more by mid-2019. And, but I was told, make no promises about timelines ever, particularly not in public. So, but 2019 is a lot can happen in a year. Okay. Yes.
Thank you. Thank you for the presentation. I'm working for an IT company, and we have bank as client. But I would like to know who are the clients for Marlo. Is it analyst, or you compare it to people who code with Excel? But do you think it's for the same type of client?
I think there are two questions in there. I think the intention is that it's code. I think in terms of specific business areas, I think that's something that we're exploring over the next few months.
Okay.
Because I think it's easy to say blockchain is a solution. What's the problem? And I think it's a matter of finding what sorts of contracts it will make sense to look at in this way. So I think I don't have an answer to that.
Okay.
What we've been looking at is ensuring that we can provide a variety of contracts.
So it's a first version.
We're working with business analysts that IOHK have employed to develop particular markets, to look at particular markets where this will be applicable. And then I think that will help us focus what we're doing. Yeah. So in a sense, it was speculative. It was technology. We've done a technology-driven development so far. We've got the technology. Now is the time to have a bit of business.
Okay. And when you are going to develop the business stuff, the partners are going to be.
I can't comment on that. I don't know, just because I'm not. I do the research.
Okay.
I'm sure there are opportunities for partnering.
Okay.
Okay, check, yes.
You can talk about that later. That's it.
Good.
Thank you, Simon. All right, so it
Also,
is.
actually, can I say one thing? We should say thank you to Alex and Pablo who are there.
Yeah.
Who have done. You know, I stand at front and talk, but they do the work.
So it is lunchtime now. So everybody, it's an hour and a half. And, to find lunch area or anything, especially places around here. So please come back in an hour and a half. Thank you.